But there is actually a simpler way to do the same thing, a simpler loss function. If you want to enforce this in the Z domain, just put a mean squared error loss on that, or absolute distance loss on whatever that's coming out of E1 and E2. And that's going to be the topic of the next paper with some modifications. Again, you want to translate from summer to winter. At the same time, you want to have some variability in your generated samples. The previous one is going to give you high quality images. That's fine. But then we know that in the winter, you can have a lot of snow, few snow, or fewer snow, or you can have trees that haven't lost their leaves yet, or they have lost most of it. So it is a one-to-many translation, and you want to encourage diversity in your generated images. And this is why it is multimodal. It is different from what we were calling multimodal when we were doing multimodal learning. Those modes were actually images, speech, text. This one is you have a multimodal distribution and to try to encourage diversity. Again, this figure is extremely important to walk through the math, but at this point in time, you're not going to understand it unless I break it apart. So there is too much information here. Let's see what we have. For each domain, you have domain 1, domain 2, summer, winter. You have generators that are going to generate summer images, they're going to generate winter images, and then you have encoders that are going to take you to the latent space, similar to what we just saw. But there is a catch here. We are going to separate the content from the style of the image. And at this point, there is no difference between content and style. We have to enforce it somehow. At this point, all you're doing is dividing a 100-dimensional vector, for instance, into 50-dimensional vectors each. You're calling one portion of it to be content, the other portion to be style. And this is what you see in this figure. You have X1, your encoder is going to give you a style, it's going to give you a content. At this point, there is no difference. You can just switch the role of them. It's just names. But then in our architecture, we are going to make sure that they have meanings. One of them is content, one of them is style. And that's going to give you two vectors for each domain. This is domain 1, this is domain 2. That's your encoder, and then you're going to have your decoder or your generators. Let's say you want to translate an image from one domain to another domain, from summer to winter. You can take an image taken in summer, push it through your encoder. That's going to give you S1 and C1. You want to keep the content because the content includes the cars, it's going to include the road. These are the big picture. It's going to have sky in it. That's the content. We're going to preserve it, but then you want to change the style. You want to make it look like winter. Same car, same sky, but same trees, but in winter. The content is the same, the style you're changing. And to change that, all you need to do is sample your style from a normal distribution. Just sample it randomly. Your generator is going to take the content of your image that was taken in summer and changes the style. That's going to give you the translation from one domain to the other domain. So assuming that our neural networks are trained, we know how to use them. This is how we are going to use it. We're going to take X1, which is going to give us S1 and C1. We keep C1. We sample S2 from a normal distribution, and then that's going to give you a translated image, X12. Or the other way around. If you have X2, you extract the content, you change the style, and then that's going to give you an image that is going from the winter domain to the summer domain. Okay? The rest of the things that you see in this figure is for training and writing down your loss function. But then I mentioned at this point in the math or in this figure, you can simply rename S1 to be C1, back and forth. How do you ensure that one of them is style, the other one is the content? You're going to use adaptive instance normalization, okay? But for now, let's see what happens. You have an image, you downsample it, you push it through a couple of residual blocks, you're going to end up with a content code. You have another branch, downsample global pooling, fully connected. That's going to give you something that you're calling style code. At this point in your architecture, you can just switch the names. You can just call this guy style, this guy the content. But from this point on, is where the meanings are going to come in. You take it, push it through a multi-layer perceptron, fully connected neural network, very boring. And these are going to give you the parameters of your adaptive instance normalization. And as soon as you have adaptive instance normalization, they're going to take the meaning of having a style. Because if you remember, when we were doing adaptive instance normalization, I mentioned that you can change the style of an image by changing the coefficient, basically the scaling parameter, and the mean to be coming from another image. And then you're changing the style. And then you go back to your residual block upsample, that's going to give you a reconstructed image. And this is, if you want to change the style, you're going to change your code here. And then you can inject or sample from something that is normally distributed. Okay, perfect. But what is adaptive instance normalization? Let's remind ourselves. Normalization is always like this. You have a feature map, or you have your features, you subtract the mean, divide by the standard deviation. This is instance normalization. So all you are doing is averaging over your pixels and computing the standard deviation over your pixels. And gamma and beta here, you can use them to change the style. And these are coming out of the MLP. They're coming out of this route. Okay, so far so good. Any questions? Was everything clear? Okay, perfect. In that case, we can move on. Now let's write down our loss function. Now that we know how to associate meanings to these two vectors, one of them is content, one of them is style. The one that is style, we're going to treat it as style. Therefore, it's going to have the meaning of a style. Now you cannot change or rename them anymore. Now let's write down our loss function. Let's see. Let's start. The loss function is going to try to train all of these. You have 6 networks. You need to train them simultaneously. Some of them are GAN type of losses. Some of them are reconstruction type of losses. Some of them are reconstructing at the pixel level. Some of them are reconstructing at the latent level. Some of them are reconstructing the content. Some of them are reconstructing the style. Let's focus on the reconstruction in the pixel domain. For domain 1, domain 2 is similar. It's just symmetric. You have an image, x1. You take it, encode it. You're extracting the style and the content. So basically, you're stopping here in your architecture. And then you're going to take that, those two numbers, those two vectors, and push them through your generator. That's going to give you a generated image. And whenever you have these dashed lines, it means that they need to match. And this is your L1 loss between the image that was the input and the image that you reconstructed. Encoder, decoder. Okay, so far so good. And P of x1 is actually sampling from your data. So you take a data point, push it through your encoder, then decode it. It has to be reconstructed. This is encoder-decoder architecture without any normalization or stochasticity. So no need for variational autoencoders. It's a simplified version of the previous paper. There is going to be some reconstruction in the latent space. And let's say you want to reconstruct C1. You took an image, X1, you encoded it. Basically, you took this route. You took X1, encoded it. It gave you the style and the content. Forget about the style, keep the content. And that's exactly what we're doing here. Whenever you see P of C1 is exactly this process. You had an image, you pushed it through your architecture, you extracted the content and the style, you got rid of the style, you kept the content. That's what sampling from P of C1 means here. And so whenever you see C1, it's the content of image 1. S2, you're going to sample it from normal distribution, from the Q here that you see. Q is just normal with 0 and identity. You have C1, content of image 1, style, which is a random style. You push them through your generator. This is what is happening here. Now you have a generated image that has the content of image 1 and some random style. You take that image, you encode it again, because this time it's an image in the second domain. You encode it, you extract the content, you extract the style, you forget about the style, you want the content to match. So whatever that's coming out of these operations is the content. It's going to give you this arrow here. And then you want the content that you started with and the content that you end up with after these operations to match. Similar thing for your style. I don't think there is any need for me to go through it. You extract the style, and then you want the style to match, okay? And then you have your GAN loss, which is gonna try to discriminate between real and fake images. But then you need to make sure where are you putting your GAN loss. You take X1, extract the content, use some random style, generate an image. This is an image in the second domain. So this is your fake domain now. This is your fake image now. And then your discriminator needs to discriminate between this fake image and an image which is real in your X2 domain. And then you can have a similar thing for X1. Is the loss clear? Okay, perfect. So all you have are reconstruction losses, which are mean absolute differences, in addition to a generative loss. And then you can generate images that look diverse. And you can look at the paper for results and then some tables. This is the meat of the paper. You can refer to the paper for good-looking images and nice-looking tables. The inception score is perhaps not the correct metric when you're conditioning on something, because you want to look at the diversity of the generated images conditioned on this scene, which was taken in summer. Therefore, you need to modify your inception score a little bit. The only thing that you're going to be changing is where you have P of Y2, it's going to be P of Y2 given X1. Given this image, look at all of the images that are generated from the second domain. And then the inception score has the diversity built into it, built into the KL divergence that you see here. Okay? This is conditional inception score. This is inception score. The only change is this conditioning here. The rest of the formulas are exactly the same. Any questions? I think I'm going to stop here. For those of you who have questions, I'll be around.